Recording started.
So there we go. So I'm just going to get my little handy-dandy pointer out here. So first of all, we're going to talk about an experiment. I don't know if you've ever seen this experiment in school before, but it's a really cool experiment, and it's basically one that shows that air can actually crush a can, which is pretty amazing, really, that air could crush a can. And so we'll talk about why that happens here. So if we think of this rectangle here as the can, there's basically two kinds of pressure that are acting on the can, okay? There's an inside pressure inside the can and an outside pressure. So the reason nothing is happening to the can when the can's just sitting there is because the inside pressure, shown by these arrows, is balanced by the outside pressure. Now the outside pressure is what you call atmospheric pressure, right? That's just basically the pressure from all the air molecules that are outside the can, okay? So they're kind of pressing in on the can, and the pressure that's inside the can is pressing against the sides of the can. And again, these two forces are balanced, so nothing really happens to the can, okay? So I said outside pressure or atmospheric pressure equals the inside pressure. And now we're going to see a different situation on the next page, because on the next page we look at what happens if we heat the can. Okay, so let's just pretend we put a flame under the can. Of course, if we've got some Coke in the can or something else, we're going to get some steam happening, right? And whenever you have steam, you have pressure. So you're going to have more pressure on the inside of the can pressing against the sides of the can. Okay? Now, what do you think will happen if the steam pressure or the pressure inside the can is greater than the pressure outside the can, the atmospheric pressure? What do you think will happen to the can? Yeah, it's going to bulge. It's going to bulge outwards, right? Now, it depends on how much greater it is than the other pressure, but if there's enough steam pressure, it could crush the can, right? It could blow it open, kind of like a bulge, right? That's what's going to happen. It's going to bulge outward, right? Okay, now we got a different situation here. Okay, what if instead of that, what if instead we put the can in cold water? Now, when we put things in the cold, they contract, right? They shrink up. So, in other words, the force on the outside is going to be greater if we put this can in cold water. Now, pretend we're not doing anything with heat right now. We're just putting it in cold water. So it's going to shrink up like anything does. When you put it in the cold, it shrinks up, and so the outward pressure is going to press in on the can, right? So the predicted result is instead of the can bulging outward, bulging really big, it's going to crush and become small in that sort of way. Does that make sense? Okay, so what happens then, I think I just accidentally went on the next page. What happens then when we do this experiment, first we heat up the can, so we get the steam pressure pressing outward, and then we quickly put the can in cold water. And when we put it in cold water, things quickly change, and so the atmospheric pressure pressing in suddenly becomes so strong that the can just crumples up. And that's what we saw in the first picture, right? So just to kind of test our understanding then, here's the first question in blue. It says the can will burst if the blank pressure is greater than the blank pressure. What do you think we would put in these blanks? One of the blanks we're going to put outward, and one we're going to put inward. What do you think we'll put in the first blank here? We're going to write outward or inward? Which pressure will be greater to make the can burst? The outward pressure or the inward pressure? Sorry. I guess, yeah, you're right. It's the inside pressure, and it's kind of pressing it outward. So I guess that could be a little bit confusing there. But we'll say the inside pressure, if the inside pressure in the can is greater than the outside pressure, or the atmospheric pressure, then it's going to burst, right? Okay. And the can is going to collapse if which pressure is greater? Inward or outward? Any ideas, Cap? Cien? That's right. The can is going to collapse if the outward pressure is greater than the inward. Okay? So does that make sense, guys? Okay, now I'm just going to quickly give you guys a video link, and you can watch this on your own. Okay, so I'm just going to paste it in the chat box, and you'll both be able to see the link, and then it'll just take like just a few seconds to watch. Okay, just so you can see what this experiment actually looks like. Okay, so if you guys click on that link, you'll be able to see the experiment, and just let me know when you're done watching that. Yeah, it is pretty cool, isn't it? Right on. So I just wanted to let you guys see that because I think it is a pretty cool experiment. So we're just going to shift gears, guys, and we're going to go to the next page here. And this page here, we're going to talk about what temperature is. So what do we really mean by temperature? Well, temperature is related to kinetic energy. Okay, so we need to talk about what kinetic energy is. So the temperature change is related to the change in kinetic energy of a substance. So what is kinetic energy? Basically, any time an object moves, it has kinetic energy. So any one of these objects that you see here has kinetic energy. Now, even snails have kinetic energy, although they move really slowly, right? But as you can imagine, the bullet is going to have a lot more kinetic energy than the snail will, right? So basically, the faster something moves, the more kinetic energy it has. Now, if we heat objects up, I noticed Jules was just typing something there. Yeah, that's right. Living things and even non-living things, right? Anything that moves has kinetic energy. Sorry about that. I'll just had the phone coming in there. Okay, so this diagram here is just showing us that as we heat objects up, they get more and more kinetic energy. Okay, so the more heat, the more kinetic energy. So when you have a solid, the particles inside the solid, they don't move very much. They just vibrate a little bit. Whereas in a liquid, they spread out and they do more kind of movements. They kind of turn around and stuff like that. And then once you get to a gas, by this point they have a lot of heat, and so they have a lot of kinetic energy, and they're zipping all over the room. Like even right now, all around your room, there's oxygen molecules that are just zipping around. Okay, so the more heat, the more kinetic energy. So we said that temperature is related to kinetic energy, so basically the higher the kinetic energy, the higher the temperature. But what is the exact definition of temperature? The exact definition is that it's the average amount of kinetic energy of the particles. So why is it the average amount? Let's look on the next page and see why average has to do with this at all. The reason is, if this was a spoonful of, let's say, water, inside that water you have some particles that have more kinetic energy than others. Like, you know, some particles might be plus 13 Celsius and some might be plus 15. So some of them have more energy than others. But the temperature of the water in this spoon is the average amount of all the particles. Does that kind of make sense? Why it's the average amount? because they all have a little bit different amount of energy. So you average it out, and that gives you the temperature. Okay? So temperature is the average kinetic energy. So with that in mind, I want to see if you guys can answer this question. So if you look at this chart here, you can see here's temperature. Temperature goes up, kinetic energy goes up. So this graph shows that temperature and kinetic energy are blank to one another. What would you put in that blank? Which one of those four words? That's right, they're related. They're not exactly identical because temperature is the average amount, so it's related. Okay? Good stuff. So let's go to the next page, and this is kind of a freaky picture here. It's talking about something called the second law of thermodynamics. I don't know if you've ever heard of the first law and the second law. Well, here's what the second law tells us. It tells us two things. It tells us that objects always go from more ordered to less ordered over time. And if you think about your bedroom, right, your bedroom tends to get more less ordered, more disorderly, I guess you could say, over time, right? Just like mine does, right? And the other thing is whenever energy is changed from one form to another, heat is always lost in the process, right? So, for instance, if you move your hands together, you've got kinetic energy going on, but you're losing heat when you rub your hands together, right? Anytime you change any energy into another form of energy, you lose energy as heat. If I hit a golf ball, I've got kinetic energy going. I'm swinging that bat or that golf club, but there's actually a small amount of heat produced when the club hits the ball. Okay, so heat is always lost rather when energy is changed from one form to another. Okay, so basically the second law of thermodynamics says that systems go from order to disorder, and another example we can think of is rocks break down into small pieces as time goes on, right? That's an example. Systems lose heat energy, and that another way of saying that is no system is 100% efficient. Okay? So if you change one energy into another energy, you always lose a little bit of heat. It's not 100% efficient. Okay? So I don't know if you guys have ever heard of a perpetual motion machine, someone trying to build one of those. Okay? This is kind of an example of one. Basically, it's a machine that's supposed to live forever, or not live forever, sorry, run forever, right? And people have tried to build those, but the reason they don't work is because of the law of the second law of thermodynamics. So again, things break down, so the parts of this machine are going to break down, and as the machine runs, it produces rust. The parts are going to break down as they kind of rub against each other, so it's not going to last forever because of the law of thermodynamics. Okay? So that's the second law of thermodynamics, and so here's kind of a question to test our understanding of it. So I want you guys to tell me which of the following is a correct statement of the second law of thermodynamics. So tell me if the first one is, it is not possible to design a process which wastes no energy as heat. Do you think that statement is true? Is it true that it's not possible to design something that wastes no energy? I know this question is it's kind of a tricky one in some ways because it's got a not possible and it's got a no energy. The correct answer for this one should be yes, it is not possible. Okay? Does that make sense? In other words, it's impossible to design a process that wastes no energy. Because, in other words, processes will always waste energy. Okay, so that's why it's not possible. So A is correct. I should have asked you about B, C, and D because it's best to kind of leave the right one until later if you can. Anyways, let's look at B, C, and D. It says systems become more and more orderly. Well, that's not true they become less orderly, right? Just like our bedroom or whatever. C says you can convert all thermal energy from an energy source into work. And that's not true, because if we're changing it from thermal energy into another energy, we're going to lose some energy along the way. So we can't ever convert all energy into something else, right? So that's not true. And this says thermal energy flows from objects at lower temperatures to objects at higher temperatures. Well, that's not true, because heat always moves from where you have a lot of heat to where you have a little heat. And you know what's interesting too? Sometimes people say, oh, the cold came in from the outside, but that's not actually true. When you get cold, it's not because the cold moved from the outside, it's because heat moved from you. If you open the door on a winter day, the heat is moving away from you to the outside, because heat always moves from where there's lots of it to where there's little of it. So you never actually have cold moving, it's always heat moving. Does that kind of make sense? Okay, and I know they had that on the Magic School Bus. I don't know if you've ever seen that before one time. They had that on one of those episodes. It was kind of cool. Yeah, Miss Frizzle was talking about that. Okay, now let's talk about something a little different. It's called heat capacity. Now when you think about the word capacity, that means how much something holds, right? So heat capacity is the ability of a substance to hold or absorb heat energy. So what do objects look like when they have a high heat capacity? Well, we know they can absorb a lot of energy, but here what I wrote in red is really important stuff to know. Okay? So an object or a substance that has a high heat capacity takes a long time to heat up and a long time to cool down. Can you guys think of anything that maybe takes a long time to heat up and a long time to cool down? Can you think of any substance? Excuse me. Okay, and you know what? Sorry about the coughing there. But that is something that most people would think. That's something that I might have thought as well. But it's actually something different, and we'll find out why in just a sec, okay? So don't feel badly, because you're not alone in that. A lot of people would think metal. Water is something that has a high heat capacity, and it takes a long time for water to heat up and a long time to cool down. So let's think of an example that helps us understand this. Okay, if you think about, say you were living in Vancouver. If you were living in Vancouver, the reason in the winter why it's not as cold in Vancouver is because when it's cold outside, the land gets really cold, but the water takes a long time to cool down. Okay? It takes a long time to lose its energy, its heat energy. So because the water takes a long time to cool down, the land is colder relative to the water. Okay? So if you're in an area like Vancouver, because you are close to water, you've got this warmer water. The water is warmer than the land because the water takes a long time to cool down, longer than the land does. So that's why it's not as cold in the winter in Vancouver. Now in the summer, it's not as hot in Vancouver as it is here. The reason is, when it's hot outside, the water takes a long time to heat up. Okay, so the land is really hot, but the water is cooler. Because again, water takes a long time to cool down and a long time to heat up. A long time to gain heat energy and a long time to lose heat energy. And that's what a high heat capacity is. When anything takes a long time to heat up and a long time to cool down, then it's got a high heat capacity. Okay? So if you think of water, that might help you remember what a high heat capacity is. And think about Vancouver, and that'll help you remember that water takes a long time to heat up and to cool down. So this diagram shows that water has a high heat capacity. Now when you look on the graph, what do you notice about the heat capacity of wood compared to steel? Which one would you say has a higher heat capacity? Okay, but on the graph we actually see that it's wood that has a higher heat capacity, right? Because this says if we go in this direction, we've got substances that have a higher heat capacity. So wood has a higher heat capacity. What that means is wood takes a long time to heat up and a long time to cool down. On the other hand, steel, like we would think about, steel takes a shorter amount of time to heat up and cool down, right? But again, remember, the definition of a high heat capacity is it takes a long time to heat up and a long time to cool down. That's why steel has a low heat capacity. Does that make sense? Okay, so I know when you first hear about heat capacity, you think, oh, it's got to be steel. It's got to be steel that has a high heat capacity, but it actually has a low heat capacity. So I just wrote down here, it seems to go against our natural understanding. But if you think about it, if heat capacity is something that takes a long time, then steel has a low heat capacity because it takes a short time to heat up. Okay, so if you look at this diagram here, you can see that the metal that's placed in something that has the same temperature throughout, the metal is going to be hot and the spoon is going to be warm, the wooden spoon, because the wood has a higher heat capacity, so it takes a longer time to heat up, and that's why it's only warm. So again, objects with a high heat capacity takes a long time to heat up, long time to cool down, long time to gain energy, long time to lose energy. All right, so let's just test this here. If we had ethyl alcohol that had a heat capacity of 2.45, and if we have steel with a heat capacity of 0.452, let's think about that and fill in the blanks. So if we were heating up these two substances and gave them the same amount of heat, which one will warm up more? Do you think the ethyl alcohol is going to warm up more, or the steel? Okay, well, remember, the ethyl alcohol has a high heat capacity, so it takes a long time to heat up. Remember, here, the wood had a higher heat capacity, so it took a long time to heat up. It was only warm, and the metal was already hot, because the metal heats up quickly. So again, that's because metal, or steel, has a low heat capacity. It heats up quickly. Okay, so does that make sense then, why it's going to be the alcohol, because the alcohol, or no, sorry, it's going to be the steel, because the steel warms up more quickly than the alcohol does. Does that make sense now, why that is? Okay, because the alcohol heats up slowly and cools down slowly. Okay, so which one do you think will absorb more energy? Think about what we said, heat capacity at the very beginning, the word capacity. Does something absorb energy if it has a high heat capacity or a low heat capacity? Okay, this one's actually going to be the alcohol, because something with the high heat capacity is going to absorb more energy. Okay, so if we look back at our definition here, we said objects with the high heat capacity hold or absorb a lot of energy. Okay, so because the alcohol has a high heat capacity, it absorbs a lot of energy. But it takes a long time to heat up. Okay, so again, the alcohol has a high heat capacity, so it takes a long time to heat up. So that's why we said that the steel is going to warm up more than the alcohol. So does it make sense, guys, what we put in these two blanks for these two questions, 5 and 6? Okay. Just, if you can remember this part, CN, if you write down sometimes, and that's good to know, if you know that certain things are confusing you, that's where you want to write it down in a notebook. And if you write it down in a notebook and put down examples, that'll help you keep the two apart. So if you write down this part in red, and then you memorize that, and you say, okay, something's got a high heat capacity, it means it absorbs a lot of energy. So if I see any question that compares two things and talks about absorbing it, I know the thing with the high heat capacity absorbs a lot. But then if I also have a question comparing two things, I know that the thing with the lower heat capacity is what is going to heat up more quickly, because things with a high heat capacity take a long time to heat up. Okay? So I think if you write this down and you also write down examples like this and think them through and think about how these examples relate to what we talked about heat capacity here, that'll help you tell the two apart. Does that make sense? Okay, good stuff. So we're just going to talk now about specific heat capacity. And specific heat capacity is a certain type of heat capacity. It's just the heat capacity we talk about when we're talking about the amount of energy required to increase the temperature of a substance by 1 degree Celsius. Okay, so when we're talking about increasing it by 1 degree Celsius, that's specific heat capacity. Okay? It's just kind of a special type of heat capacity. Okay, now guys, I think maybe we should take a break for a little bit. Do you guys want to get a drink or something like that? Okay. How about you, CN? Alrighty. Well, we will continue then. If you do need to get a drink at some point, just let me know, okay? Now, we're going to talk about something here having to do with work, the concept of work in science. And it's kind of a funny concept. I'll tell you why. Let's pretend this guy, we'll call him Joe. Let's pretend he's pushing against a fridge here. Now, if he pushes against that fridge with all his might, and that fridge does not move, according to what science calls work, he doesn't do any work. Now that sounds kind of frustrating for Joe, right? He pushes against his fridge with all his might, but if it doesn't move at all, he's done no work. Okay? Kind of sounds weird, right? Now, the reason it is because work is equal to force times distance. Now, Joe's pushing with a lot of force. He's got that going on for him, because a force is just a push or a pull on an object, right? He's got all kind of force, but there's no distance. And so because he has no distance going on with the fridge, there's no work. For work to be done, there has to be both force and distance, okay? So this guy, on the other hand, is pulling, and he pulls this chair 1 meter. So in this situation, he is doing work because he's got both the force, that's the pull, and he's moved it a distance, that's 1 meter, okay? So work in science always means that you've got force and distance, and they're multiplied by each other. So we'll go through an example here of a problem that involves work. So Joe is moving a couch, and he moves at a distance of 3.4 meters with a force of this many newtons. And we'll talk in a bit about what that means. This is scientific notation, right? The question says, how much work does he do? So that's what we want to find, how much work he does. Now, it's always good when you're solving any kind of math or science problem, write down the information you're given and then write the solution. So what info are we given? We're given the distance, so we write that down, and we're given the force, so we write that down. Now, we can, if we want, we can figure out what does this actually mean in regular math. Remember that 10 to the power of 3 means we multiply 10 by itself 3 times, right? In other words, 10 times 10 times 10. That's what 10 to the power of 3 means, right? Okay, so really we're multiplying 4.5 times all those 10s. 10 times 10 times 10 is 1,000, right? So we're really multiplying 4.5 times 1,000, which gives us 4,500. Okay? That's how you can figure out what 4.5 times 10 to the 3 is. Okay, so we know we're given those two things, a force and a distance. And we can find the work, because we know work equals force times distance. So we write down force, write down distance, and we just rewrite this here as 4,500 newtons. Force is measured in newtons. Okay? So now we would put this on our calculator, 4,500 times 3.4, and we would get 15,300. Now the units for work are joules. Okay? So remember, work is always measured in joules, and energy is always measured in joules. And I'll tell you why that makes sense, that both work and energy are measured in joules. The reason is the definition of work. Work is the transfer of mechanical energy from one object to another. So let's give an example here. Okay, let's say a golfer hits a golf ball. First, the golfer has a lot of energy in their arms, and so the golfer swings the club. So we say the golfer does work on the club. Okay, they transfer energy from their body to the club. Okay, so again, we can see work and energy are involved there, and then the club does work on the ball, right? So again, work is the transfer of energy. So again, it makes sense that both are measured in the same units, which are joules. Okay, so let's look at a problem here where you guys are going to solve it that involves finding work. So it says, when pushing her younger brother on a swing, Megan exerted an average force of 2.3 times 10 to the power of 2 newtons through a distance of 62 centimeters. How much work does Megan do? And I put, hint, distance needs to be in meters. Okay? So it's in centimeters. We're going to have to change it into meters. So why don't we do that first of all? What is 62 centimeters going to be in meters? What's the magic number that we use to change from centimeters to meters? Do you know, is that magic number 10, 100, 1,000? Any idea? That's right, because there's 100 centimeters in a meter. So if we want to change 62 centimeters into meters, are we going to divide by 100 or multiply by 100 to find the number of meters? That's right. So we're going to divide 62 by 100, and that's going to be 0.62 meters, right? So I'm just going to write that below here, 0.62 meters. Okay, so now things are looking a little better. And can you guys tell me what 2.3 times 10 to the power of 2 is if we change that into a regular number? What does 10 to the power of 2 equal to? 10 is multiplied by itself 2 times, so 10 times 10. Okay, so that's going to be 100, right? And we multiply 100 by 2.3, and we're going to get 230. Okay, so that's what that means. Okay, so we've got force and we've got distance. So can anybody tell me what we're going to do with those numbers of force and distance to find our answer of work? That's right, we're going to multiply, and what do we get when we multiply those two numbers? You guys have your calculators with you? Okay, 142.6, and CN, can you tell us what units will that be in? That's right, it's going to be in joules. Good stuff. So I'll just review what we did here then. We multiplied, we said work equals force times distance. We multiplied 2.3 times 10 to the power of 2 times 0.62 meters, because we changed centimeters into meters. And then we did those on our calculator. Again, 10 to the power of 2 is equal to 10 times 10, which is 100 times 2.3. That's 230. Multiply 230 times 0.62. Does that make sense, guys, all the steps we did to solve this one? Okay, good. All right. Jules, is there any step you want us to go over? Okay, so again, we want to multiply force times distance, right? Work equals force times distance, because we're trying to find work. And so underneath force, we put down the force we're given in the problem, because it says it has a force of this many newtons. And underneath the distance, we write down 0.62 meters, because we changed centimeters into meters. We divided by 100 to do that. So does that make sense, what we have at this point here? Okay, and then we just multiply these two numbers together. This turns out to be 230, and we multiply 230 times 0.62. Does that make a little more sense? Okay, and what I think would really help, guys, is again, after we're done this, I'll have the file that we're working on right now, the PDF file, and you can try all of these again on your own. I'd really encourage you to do that. And if there are any you can't get, feel free to let me know, and I can try to help you again, either through email or we can do another one of these sessions. And, you know, so just to make sure that you can get all of these on your own, okay? So, before the last question, we used the work formula and we solved for work. So I put work equals force times distance, and I put a question mark there, because what we were trying to find was work, and we didn't know what it was. That's why we put the question mark there. So we were given force and distance, we need to find work. Now what we're going to do, we're going to use that same work equals force times distance formula, but we're going to find distance instead. So here I put work equals force times question mark, because we don't know what the distance is. Okay? So that's what we're going to do in this next problem. So in this problem it says Jill shoots a puck with a force of 7.5 times 10 to the power of 2 newtons and does 10,500 joules of work. How far did she shoot the puck? So now I could have written the given up above, and I probably should have done that. But our solution here is always going to involve, first of all, writing out the work formula. Work equals force times distance. Now we know what force is, so underneath force we write 750 newtons, because we figure out that's what this is. We know what work is, because we're told it's this many joules of work. What we don't know is distance. So far we know this much of the formula. We filled in the numbers when we knew what they were. So we want to find distance. So, are you guys familiar with the steps in solving equations? Okay, well let's review it for this equation anyways. Now, what we want to do is we want to end up with distance on the right side of the equation. We want to find out what it is all by itself. So we're going to end up with like distance equals some number on the left side. But the problem is right now we have distance times 750. We don't want that 750. But to get rid of times 750, what is the opposite of times? That's right, the opposite of times 750 is divided by 750. So that's why we're dividing the distance times 750 by 750, because the opposite of times is divided by. Now if we do that to the right side of the equation, we need to do it to the left side, because it's like a teeter-totter, right? If we do something to the one side, we have to do something to the other side, so the whole equation stays balanced. So we divide both sides by 750. When we do that, we get rid of the 750 on the right side, because any number divided by itself gives you 1. You know, 5 divided by 5 gives you 1, 10,000 divided by 10,000 gives you 1. So because of that, we can cross off the 750, and we're left with distance on the right side, which is what we're trying to find. On the left side, we just have to do a division on our calculator. So when we divide those two numbers, we get 14. So we end up with distance equals 14. So does that make sense, guys, how we solve for distance using the work formula and using solving equations? Okay, well let's give you a chance to practice what we just did on the next question. So the next question says, Johannes uses a wheelbarrow to move soil from his garden to a new flower bed. It says he exerts an average force of 172 newtons, so I underline that part because that's important, while pushing the wheelbarrow, and he does 8.3 kilojoules of work. Oh, kilojoules, that sounds a little different, right? So we'll kind of keep that in mind. So we have force and we have work, and the question says, how far is he moving the soil? That's what we're trying to find. We're trying to find distance. So I put hint, use the formula work equals force times distance to solve for distance. And remember, work needs to be in joules. We have kilojoules, right? Okay, so first of all, we need to start with our formula, right? We always start with that. So I'm going to write work equals force times distance. Okay, now beneath work or force or distance, what can we write? Which ones are given in the problem? Can you guys tell me which were given? Are we given work, force, or distance? There's two of them that were given. So if you could tell me which were given and how much that amount is. Okay, so force is 172. I'm just going to write the number here. Is there something else we're given? Can you see anything else, Jules? Another number that we're told? Okay, 8.3, and what is that? What is 8.3? What does that stand for? Okay, and does it stand for work, force, or distance, the 8.3? Okay, that stands for work. So underneath work, we're going to write 8.3 kilojoules. Now, remember, it has to be joules, right, to use this formula. Do you know how many joules that is? Think of it this way. If I have 8.3 kilometers, how many meters do I have? Well, let's start with, let's say we have 1 kilometer. If I have 1 kilometer, how many meters do I have? Okay, so if I have 8.3 kilometers, how many meters do I have? So if 1 kilometer is 1,000 meters, if I had 8.3 kilometers, how many meters would that be? Good. So if I have 8.3 kilojoules, how many joules do I have? It would be the same thing, right? It's going to be 8,300 joules. Does that make sense? Because kilo just means 1,000 of something. So if I have 8.3 kilojoules, the kilojoules means 1,000 joules, and the 8.3 means 8.3 times that. So does that make sense, guys, that we have 8,300 joules? Okay, good stuff. So we know then that we have 8,300 joules equals 172 times the distance. Okay, so that's what we have so far in our formula. Does that make sense so far, guys? I'm just going to assume it makes sense unless you stop me, okay? So we have 8,300 joules equals 172 times the distance. So can somebody tell me what we do next to solve this equation? We want to end up with distance on the right side. So what are we going to do to end up with distance on the right side of the equation? Okay, we're going to cross out the 172. And what allows us to cross out the 172? What do we do first of all? Do you know what math operation, multiply, divide, add, subtract, we do to both sides? The opposite of multiply. Yeah, we're going to divide both sides because we're multiplying by 172. The opposite of multiplying by 172 is divide by 172. And so then, like you said, we're going to cross off. So now here's the point we can cross off. Now that we've divided both sides by 172, we're left with distance on the right side. And then we just have to do the math, right? And we won't actually do that right now. We could just divide 8,300 by 172. Okay? So does that make a little more sense, guys, now that we've had a chance to practice this one again? Okay. And so that was that question here. Now I'm just showing all the steps here, right here, okay? We could have actually divided out when we had the variables or the letters before we even put the numbers in. We could have ended up with this formula and then plugged the numbers in. That's the way I did it this time. It's similar to the other way of doing it, right? Okay, and so you could try this out and get this actual answer here. Let's talk then at this point about the fact that work is the area under a force versus distance graph. Okay, so this is a force versus distance graph. Okay, so force is on one axis of the graph, distance is on the other. Now, why is work the area under the line that's on the graph? Well, the reason why it is because work equals force times distance, and force is this side, right? So however big this side is, that's force. Distance is this side. So it's like a rectangle, right? The rectangle is length times width. So force times distance gives you area. Area is what's shaded in here, right? The area of this rectangle. So that's why the area under a force versus distance graph is work, because you're multiplying force times distance, which is like length of a rectangle times width of a rectangle. Okay, so I just wrote that underneath. I wrote work equals force times distance on this graph, and work is the same as area, and the area is equal to the length times the width. Does that make sense, guys? Okay, so if we find the area under a force versus distance graph, it gives us the work. So here's an example of a force versus distance graph. Let's say we had a problem here, and it says, what's the amount of work? Looking at this graph, what would the amount of work be? Well, it would be equal to the force, which is 10, times the distance, which is 4. 10 times 4 gives us 40. Okay? So area equals length times width, or force times distance. 4 times 10 is 40. Okay? So that's how we would find the amount of work. We would find the area by length times width. All right, so this question here, we have a graph that's a little more complicated because we kind of have two parts of the graph. It says find the amount of work done on this graph. So it's the area under the whole graph, but that's made up of two shapes. It's made up of a triangle shape, so we're looking at this area added to this area of a triangle plus the area of a rectangle. So let's review how we find the formula for the area of a triangle. Well, if we look at the area of a rectangle, we know the area of a rectangle is always height times base, right? So if the area of a rectangle is height times base, you can tell just by looking at this diagram that the area of a triangle is half as much as the area of a rectangle, right? Just looking at it, you can tell it's half as much. So if the area of a rectangle is equal to base times height, the area of a triangle must be equal to 1/2 base times height. And we put the base times height in brackets because we multiply them together and then we find out what a half of that is. Okay? So area of a rectangle is base times height, area of a triangle is 1/2 base times height. So those are the formulas we need to solve this problem, because what we're trying to do is find the area of this rectangle and the area of this triangle. So we're going to add those two together. So to find the area of this triangle, how much is that going to be? It's going to be 1/2 base times height. Okay? So I'll just write that down. The area of the triangle is 1/2 in brackets base times height. So can you guys tell me what the base of that triangle is going to be? How long the base is? That's always the bottom line. Okay, the base is going to be 2, and what's the height going to be? Okay, the height's, I wasn't sure if that 2 was the base, or would you agree that the height is going to be 2 as well. I'm not sure if that was the second 2 was meant as the height. The height's going to be 2 as well, right? Okay, so we've got the area of the triangle. We just need to figure out what a half times 2 times 2 is. Now we're going to put plus because we're adding the area of the rectangle. So the area of a rectangle is base times height. It's not a half base times height. What's the base of the rectangle going to be? How much? Well, remember, to find the base, we're going to subtract 10 minus 2. That's how big this is, right? It's 10 minus 2. So, and how much is that? Okay, 10 minus 2 is going to be 8, right? So the base of the triangle, or the rectangle, is 8. Does that make sense? Excuse me. Okay, and how much is the height of the rectangle? Okay, it's also going to be 2. Good. So now we can find out the area of the triangle. It's going to be 1/2 times 2 times 2. So 2 times 2 is 4, and 1/2 of 4 is going to be 2. So 2 is going to be our area of the triangle. Now to find our area of the rectangle, it's 8 times 2, which is going to be 16. So we add the area of the triangle, which is 2, to the area of the rectangle, which is 16, and that's going to give us 18 as the total area. Does that make sense, guys? Okay, good stuff. So now this here is just solving the same thing. Okay, it's just going over the same solution. So again, you could look on the PDF file if you want to see the full solution. Now, one thing I wanted to talk to you guys about is to cover all the material that's on the test. First of all, I don't think we'll be able to cover all of it today because it does take quite a while to go over. And I want to ask you guys if there's another day this week that might work for you guys to finish all of it, finish the rest of it. Like for instance, today's Tuesday. Does tomorrow work for doing this again? Okay. Does Thursday work okay with you as well, Jules? Okay, awesome. So that's good, and that gives us a break between the 2 days as well, right? That's good. I just have to think for a second here now. Before I say anything, let me think. Does my son have a game or something on Thursday? I think I should be good for Thursday. Pretty sure. Okay. So guys, we do still have some to cover, even just in this session today. And I know it's already been an hour. So I want to ask you guys: do you want to get a drink at this point, or just kind of take a break for a few minutes at this point? Okay. Does that sound good for you, Jules? Just to take a little bit of a break and get a drink or whatever? Okay, good stuff. So why don't you guys come back in about 5 minutes and we'll finish this stuff off, and then you guys will be able to go. So once you guys are back, if you just type your name back in the box. Okay, hi CN. Are you back as well, Jules? Okay, awesome. So, guys, thanks for your hard work in this. I know doing this at nighttime is, I know you've already done a full day of school, and I do appreciate you coming to the session. And so we'll do another at least 15 minutes or so, and see how we feel after that. Okay. It's just there are quite a few concepts to go over, and so I think we'll just see how we're doing after about 15 minutes. Okay. All right. So we're going to talk about something called displacement. So this question is going to deal with that. Now I'll kind of explain that before we even get into this problem. Displacement is the overall distance you are from where you started. Okay? So let's say you ran a race that looked like this. That's the distance. The distance is the whole race that you run. Whereas displacement is only the distance from where you started to where you finished. So you don't take into account all this, you just go the straight line distance from where you started to where you finished. That's what displacement is. So displacement is the overall, I shouldn't say distance, it's not good to mix together those two words. So I should say it's the overall measurement from start to finish. Okay, does that make sense? That's what displacement is. So this question here says Brooks is 220 kilometers south of Hannah and Killam is 109 kilometers north of Hannah. What is the displacement from Brooks to Killam? Okay, so again, we've got the problem written again here. So what we need to do is we need to label these points. Each one of these points stands for one of these cities or towns, and we need to label which one we think goes where. Okay, so we have 3 in this problem. We have Brooks, Hannah, and Killam. So which one do you guys think goes in the middle based on reading this problem? It says Brooks is 220 kilometers south of Hannah and Killam is 109 kilometers north of Hannah. What is the displacement from Brooks to Killam? So which one of those 3 towns do you think goes in the middle? That's right, because one of them is south, Brooks is south of Hannah, and Killam is north of Hannah, so Hannah goes in the middle. So we'll just label Hannah first of all. It makes sense to start with Hannah. And so which one are we going to label north of Hannah? Okay, so it's Killam. So Killam is north, and of course that leaves the last one, which is Brooks, is going to be south. Okay, so now let's take the problem and kind of break it down. And sorry, on my screen I just need to be able to get all these to fit at the same time. Okay, so it says Brooks is 220 kilometers south of Hannah. So what we need to do is draw an arrow that shows us that. So since Brooks is 220 kilometers south, we draw an arrow, and we are going to label that arrow with 220. Sorry, my thing is not working here. We're going to write 220. Sorry, my computer is just starting up another program because I accidentally started something else. All right, so we're going to label this as 220 because Brooks is 220 kilometers south, and we're told that Killam is 120 kilometers or 109 kilometers north. So we're going to write another arrow from Hannah, and that's going to be 109 kilometers north. Okay, so sorry, this is not wanting to cooperate. There we go. 109 kilometers. So the question says, what is the displacement from Brooks to Killam? So here's Brooks down here. Here's Killam up here. What do you think the displacement will be? So what are we going to do with these two numbers, 109 and 220, to find the displacement from Brooks to Killam? That's right, it's going to be 329 kilometers, because we're going to add the two together and find the overall displacement. Okay? Does that make sense, Jules, as well? Okay. So does this one make sense, Jules? But the total displacement from Brooks to Killam is going to be 329, which is 109 added to 220. Okay, so basically we had to draw the diagram. We drew it by drawing 3 points. We decided which one was in the middle. Then we decided which one was north and labeled that, which one was south and labeled that arrow. And then we got a better picture of what was going on when we're talking about the displacement from Brooks to Killam. Now the next question is another one that's displacement, but it's kind of a different one. This one says Raja drives east of Olds to Trochu, a distance of 54 kilometers. He then drives west to Sundre, a distance of 92 kilometers. What is his total displacement? So, again, we need to draw the 3 points and decide which one's in the middle. Now, which one do you think is in the middle? Well, you know what sometimes helps when we're not sure which one, we can just start with where we are, okay? So if we start, yeah, it's actually going to be Olds, and here's how we figure it out. We start at Olds because it says we're going east of Olds to another place. So we start at Olds. So the best way to do it is really start with what you have in the beginning. You have Olds, and then you're going to go east. So we label Olds, and then we write, show an arrow going east. And it says that's going to be Trochu. So now we label Trochu here, and we label how far we've gone, which is 54 kilometers. Okay? After that, it says he's going to drive west, so the other direction. And it says he's going to go to Sundre. Now it says he's going 92 kilometers, which means that this arrow is going to be longer than the other one in the other direction. Okay? And this arrow is going to be showing us where Sundre is. Does that make sense how we did that, guys? Okay, good. So just start with the info you have east of Olds, and you label that, and then go with the next info. So the next info is 92 kilometers rather, west. So there's our diagram. And so since we have our diagram, it says what is his total displacement? So what math do you think we're going to use to find the total displacement? Are we going to add like we did the last time? Add the two numbers? Well, we're actually going to subtract this time because our total displacement, remember, is always the distance from where we started, and that's here, to where we finished, and that's here. So that's a smaller amount than the 92, and what this amount equals is actually 92 minus 54. Okay, so if we subtract off the 54 from the 92, the part we're left with is this part here. Does that make sense? Okay, so it's 92 minus 54. And 92 minus 54 is going to be, sorry, just a sec, is going to be 38. Okay, so the overall displacement, in other words, the overall measurement from start to finish, is going to be 38, and it's going to be west. So when we put our answer down, we should say 38 kilometers west. That's our answer. It's got to include west as well. Okay? Does that make sense how we did this one, guys? Okay, so that's displacement. And what we're going to talk about now is acceleration. And acceleration is different from velocity. Velocity is kind of a similar word to speed. The only difference between speed and velocity is velocity has to do with direction as well as just numbers. You know, so if you say 3 meters per second, that's kind of like speed, but if you say 3 meters per second west, that's velocity, okay? And now, so if something's traveling at a constant velocity, that's kind of like a constant speed. So let's say my arrow here is kind of a constant velocity. That's like a car driving down the highway. Acceleration is when you go faster and faster. Okay, so when you're trying to pass another car, you accelerate. So if you look at my arrow now, it's accelerating because it's getting faster and faster. Okay, so that's the difference between velocity. Constant velocity is like constant speed. Acceleration, constant acceleration, is when you go faster and faster. Okay, the formula for acceleration is the change in velocity divided by the change in time. Okay, so change in v divided by change in t. Now, one example of acceleration in the world around us is objects falling towards the earth. Okay, all objects, when they fall towards the earth, fall with an acceleration of 9.8 meters per second squared. Okay, meters per second per second. What that really means is every second they go 9.8 meters per second faster. Okay, so if 1 second they were going 9.8 meters per second, in the next second they're going 19.6 meters per second. And then in the next second you add another faster. Okay? So they're going faster and faster every second. That's acceleration. And the formula for acceleration is change in velocity divided by change in time. So if we're doing a question that involves that, like this one here, here it says there's a velocity of 163.05 meters per second in 5.23 seconds. And I think maybe we should make this our last question because we've had a pretty long night so far. Okay? So acceleration is equal to change in velocity divided by change in time. So basically all we need to do is on the top, we write what the velocity is. That's 163.05. So I'm going to write that in, 163.05. And change in time, we're told that's 5.23 seconds, 5.23. So now we just do the math, and I think I've got that on the next page here. The math, when we divide those two, we're going to get 31.18 meters per second squared. Okay, so that's our answer for acceleration. All right, so so thanks guys for going through with these. We'll cover some more of these on Thursday at 6 o'clock, since it sounds like that works best for you guys. And again, thanks for your answers on this. And if you practice these ones on the PDF file again, that will really help you when it comes time to do the test. Okay? Alrighty. You betcha. Well, hope you have a great rest of the night. God bless you guys, and I will chat with you guys again on Thursday.